When the Hubble telescope launched in 1989, it promised to expand our understanding of the universe with every picture it took. After 30 years of service, it did exactly that. From observing distant stars and galaxies, to measuring the exact age of our universe, Hubble answered so many questions. Now it's time to answer the next set of questions as we continue to uncover the mysteries of our universe. In this video, we're going to look at the James Webb Space Telescope. We're also going to look at what it will observe and how it could find the most Earth-like planets, with the highest chance of supporting life. After 30 years and millions of pictures later, the Hubble telescope has peaked in terms of how far back into the universe it can observe. Hubble's furthest observation was made in 2016, when it captured an image of Galaxy GNZ11. This galaxy is 32 billion light-years away, but due to the expansion of space, the light we see from it shows the galaxy as it was 13.4 billion years ago. Although this is just 400 million years after the Big Bang, Hubble is unable to see anything further than this since it's limited by the range of wavelengths it can observe. As the light from distant galaxies travels from one point to another, its wavelength is stretched by the constant expansion of space. By the time the light reaches Hubble, it's stretched to a wavelength outside of Hubble's viewing range. Anything that's stretched to a wavelength above near-infrared is unobservable by Hubble. In order to observe the most distant and earliest objects in our universe, we need to observe the infrared light that comes from them. This is where the James Webb Telescope comes in. When development began in 1996, many of the technologies needed for the telescope had yet to be invented. An enormous sunshield is required to keep the telescope at an extremely low temperature. Special wavelength sensors that can operate at cryogenic temperatures also had to be developed for this telescope. James Webb will observe primarily in the infrared range, which will allow it to see things that Hubble couldn't see. When stars and planets are first forming, they're often hidden behind enormous clouds of dust which absorb visible light. Hubble is able to observe these magnificent clouds, but it can't see what's going on behind them. This is the famous Pillars of Creation Nebula, which Hubble imaged in 2014. Observing it in infrared light reveals just how much is going on behind these dusty clouds. But James Webb won't be the first infrared space telescope. Over the years, there have been several infrared telescopes in space, but none of them have had the detail and capability that James Webb will have. The resolution of a telescope is limited by the number of wavelengths it can fit across its mirror. A larger mirror allows for a higher resolution. The Spitzer infrared telescope has a mirror just 0.85 meters in diameter. Hubble's mirror is slightly larger at 2.4 meters, but James Webb will have an enormous mirror, measuring 6.5 meters wide. This will give the telescope an incredibly precise resolution, capable of observing a penny from 40 kilometers away. This level of precision will be required if it wants to discover the most distant galaxies and planets in our universe. One of the most impressive goals of the James Webb Telescope is to find and analyze the most distant Earth-like planets in our universe. To do this, James Webb will focus on a single star which is known to have planets orbiting it. As a planet crosses in front of the star, the telescope will measure a small dip in light. At first, this will help to determine the size of the planet, but measuring dips in multiple wavelengths will give us even more information. Since atoms and molecules absorb light at different wavelengths, measuring dips at specific wavelengths will signify which molecules are present in the planet's atmosphere. If the telescope measures a dip in light at around 1.15 and 1.4 micrometers, we can tell that the planet's atmosphere contains water vapor, since H2O absorbs a larger amount of light at those wavelengths. James Webb will be able to observe a large range of wavelengths from visible light through to mid-infrared. This will be perfect for detecting various kinds of molecules that are common on Earth like CO2, oxygen and nitrogen. Along with Webb's incredible sensitivity, it will be able to discover extremely distant planets that bear an uncanny resemblance to our own. Finding these Earth-like planets will teach us more about our own planet, while taking us one step closer to proving that we are not alone in this vast cosmic arena. So as we patiently wait for the James Webb Telescope to be launched, we can look forward to the incredible scientific discoveries it will make. Engineers working on NASA's James Webb Space Telescope have successfully folded and packed its Sunshield for its upcoming million-mile, roughly 1.5 million kilometer journey, which begins later this year. The Sunshield, a 5-layer, diamond-shaped structure the size of a tennis court, was specially engineered to fold up around the two sides of the telescope and fit within the confines of its launch vehicle, the Ariane 5 rocket. Now that folding has been completed at Northrop Grumman in Redondo Beach, California, the Sunshield will remain in this compact form through launch and the first few days the observatory will spend in space. Designed to protect the telescope's optics from any heat sources that could interfere with its sight, the Sunshield is one of Webb's most critical and complex components. Because Webb is an infrared telescope, its mirrors and sensors need to be kept at extremely cold temperatures to detect faint heat signals from distant objects in the universe. In space, one side of the Sunshield will always reflect light and background heat from the Sun, Earth and Moon. Thermal models show that the maximum temperature of the outermost layer is 383 Kelvin, or about 230 degrees Fahrenheit. Meanwhile, the other side of the Sunshield will always face deep space, with the coldest layer having a modeled minimum temperature of 36 Kelvin, or about -394 degrees Fahrenheit. Fully deployed, the telescope's Sunshield measures almost 70 feet by 47 feet 21 meters by 14 meters. When stowed inside the rocket for launch, the folded Sunshield will be packaged in a very confined area in between other structures of the observatory, to accommodate the limited space inside the 18-foot 5.4-meter diameter rocket fairing. There is nothing really analogous to what we are trying to achieve with the folding up of a tennis court-sized Sunshield, but it is similar to packing a parachute, said Jeff Chisholm, a lead Sunshield design engineer at Northrop Grumman. Just like a skydiver needs their parachute packed correctly in order to open perfectly and to successfully get back to Earth, Webb needs its Sunshield to be perfectly stowed to ensure that it also opens up perfectly and maintains its shape, in order to successfully keep the telescope